On the night of December 27th, 2004, something reached across the galaxy and touched the Earth. No one on the ground noticed. It was the week between Christmas and New Year's, and most of the world was asleep or finishing leftovers or watching the news cycle wind down after the year's last headlines. But 50,000 light-years away, in the constellation Sagittarius, on the far side of the Milky Way, an object no larger than a city had just released more energy in 1/10 of a second than our Sun will produce in 150,000 years. The radiation had been traveling for 42,000 years before it arrived. It left its source when Neanderthals still walked Europe, when the cave paintings at Lascaux had not yet been imagined, when every human being alive was a hunter-gatherer who had never seen a wheel. And when it finally reached us, it did not knock politely. The gamma-ray detectors aboard NASA's Swift Observatory, instruments specifically built to measure the most violent bursts of radiation in the cosmos, were immediately overwhelmed. They saturated, blinded by a signal far beyond anything they were designed to handle. The European Space Agency's integral satellite went dark for 7/10 of a second. The RESI Solar Observatory, which was pointed in an entirely different direction, recorded the blast anyway because the radiation was so intense that it bounced off the moon and arrived from behind. Within moments, every gamma-ray instrument orbiting the Earth had either saturated or shut down. These were machines built to stare into the heart of the most energetic events in the universe, and this one made them flinch. Down on the surface, the effects were more subtle but no less real. The burst of gamma radiation compressed the Earth's ionosphere, the thin, electrically charged shell of atmosphere that sits between 60 and 1,000 kilometers above your head, and briefly expanded it, altering its chemistry in ways that took weeks to fully measure. Fishermen in the Arctic reported seeing a sudden aurora in the sky, a shimmer of light that had no business being there at that hour, in that season, at that latitude. The night side of the Earth had, for a fraction of a second, been pushed a little closer to day. The source of all this was an object 20 kilometers across, not 20,000, not 20 million, 20. Smaller than London, smaller than most cities you have driven through without stopping, and it had reached across 50,000 light-years of empty space to physically alter the atmosphere of a planet it had never been anywhere near. That object was a magnetar, and the question that matters, the question this documentary is really about, is whether magnetar deserves the title that astronomers, with some reluctance, have given it, the most dangerous object in the universe. It is a serious claim. Black holes are terrifying, certainly, but they are passive predators. A black hole sits in space and waits for something to wander too close. It does not reach out. It does not explode without warning. A supernova is catastrophically violent, but it happens once, a single detonation, and then it's over and the danger passes. Even gamma-ray bursts, for all their ferocity, are one-time events. The death scream of a collapsing star, aimed in a single direction, gone in seconds. A magnetar is different. A magnetar is actively, repeatedly, unpredictably dangerous. It erupts, settles, and erupts again. Its magnetic field, the strongest of any known object in the universe, doesn't just pull on nearby matter the way an ordinary magnet does. It deforms atoms into shapes that should not exist. It bends the fabric of empty space itself, turning the vacuum into something that behaves like a crystal. It cracks its own surface in events called starquakes, releasing floods of radiation that can be detected from the other side of the galaxy. And it does all of this within an active lifetime of roughly 10,000 years, which in cosmic terms is less than the blink of an eye. A brief, furious tantrum from an object that packs more destructive potential into its 20-kilometer frame than anything else the universe has produced. There are roughly 30 confirmed magnetars in our galaxy. There may be more than 1 million that have gone quiet, drifting unseen through the dark. The closest known one is 9,000 light-years away, comfortably distant by any reasonable standard. But comfortably distant is a phrase that loses its reassurance when you remember what happened on December 27, 2004, from 50,000. There is something worth pausing over before we go any further. The object that shook our ionosphere that night is, in every meaningful sense, unknowable through direct experience. You cannot visit a magnetar. You cannot observe one up close. If you somehow approached within 1,000 kilometers, the magnetic field would distort the electron clouds of every atom in your body, and the chemistry that holds you together would simply stop working. Long before that, at a distance halfway from the Earth to the Moon, every credit card on the planet would have been wiped clean, though by that point, credit cards would be the least of your concerns. And yet, we know this object exists. We have measured its magnetic field, timed its rotation, catalogued its outbursts, and built theoretical models that predict its behavior with remarkable accuracy. We have done all of this from the other side of the galaxy, using instruments that can be blinded by the thing they are trying to study. The fact that we know anything at all about magnetars is itself a kind of monument to what this particular arrangement of carbon and water and electricity, this thing we call consciousness, is capable of when it turns its attention to the universe. But before we take this journey together, from the death of a star to the birth of a monster, from the physics of impossible magnetic fields to the moment when a magnetar's fury crossed the galaxy to reach us, I want to ask you for something. If this is the kind of story that speaks to you, if the idea of spending 2 hours exploring one of the strangest and most violent objects in the cosmos sounds like exactly the right way to spend your evening, then I would be genuinely grateful if you subscribed to this channel. Not because an algorithm demands it, although it does, but because there is more of this coming, and I would like you to be here when it arrives. And if you have a moment, leave a comment. Tell me where you are listening from tonight, what time it is where you are, what brought you here. I read every single one of them, and they are, without exaggeration, the reason this channel exists. Now, to understand what a magnetar is and why it holds the title it holds, we first need to understand where it comes from, because a magnetar is not something the universe builds from scratch. It is what remains after something far larger has been destroyed, the compressed, superheated, unimaginably dense remnant of a star that lost its longest battle. And that battle between gravity and everything else is where our story begins. Every star that has ever existed is fighting the same war. On one side, gravity, pulling inward, trying to crush the star into the smallest possible space. On the other, the nuclear furnace at the star's core, pushing outward with the energy of millions of hydrogen bombs detonating every second. For most of a star's life, these two forces hold each other in a delicate, furious balance, and the star shines because of it. The warmth on your face when you step into sunlight is the visible evidence of a battle that has been raging for 4.5 billion years. Our sun will fight this war for another 5 billion years before it runs low on fuel, swells into a red giant, and eventually collapses into a white dwarf, a dense, cooling ember about the size of the Earth. It is a quiet death, as stellar deaths go. Unremarkable. The kind of ending reserved for average-sized stars in average-sized galaxies. But there are stars that burn far hotter and far faster. Stars born with 10 or 15 or 25 times the mass of the Sun, and their deaths are nothing like this. These massive stars tear through their hydrogen fuel in a few million years rather than billions. When the hydrogen runs out, they fuse helium. When the helium runs out, they fuse carbon, then neon, then oxygen, then silicon. Each new fuel burns hotter and faster than the last, and each one buys the star a little less time. Hydrogen fusion sustains a massive star for millions of years. Silicon fusion lasts about a single day. And when silicon fusion ends, what it produces is iron, and iron is where the road stops. Every element lighter than iron releases energy when you fuse it. That released energy is what pushes outward against gravity, what keeps the star inflated, what prevents the whole thing from caving in on itself. But iron is different. Fusing iron does not release energy, it absorbs it. And so when a massive star builds an iron core at its center, it has effectively built its own death sentence. The furnace is still burning in the shells above, layered like an onion, silicon around the iron, oxygen around the silicon, and so on. But at the very heart of the star, the thing that has been holding gravity at bay for millions of years has just quietly stopped working. What happens in the next fraction of a second is one of the most violent events in the known universe. The iron core, no longer supported by outward pressure, begins to collapse. And it does not collapse slowly. Within a quarter of a second, the core reaches velocities approaching a quarter of the speed of light, 70,000 kilometers per second, as gravity, unchecked for the first time in the star's entire existence, pulls everything inward with absolute authority. The core, that was roughly the size of the Earth, is crushed into a sphere about 20 kilometers across. A volume that could comfortably contain a mid-sized city now holds more mass than the Sun. The density becomes so extreme that a single teaspoon of this material would weigh over 100 million tons, more than the mass of every building, vehicle, and human being in a large metropolitan area, compressed into a space you could balance on your fingertip. At these densities, atoms themselves cannot survive in their normal form. Protons and electrons are forced together, merging into neutrons, and the entire core becomes a single, unimaginably dense ball of neutron matter, a neutron star. The outer layers of the dying star, still falling inward, slam into this incompressible neutron surface and bounce outward in a shockwave that tears the star apart from the inside. What follows is a supernova, a detonation so luminous that, for a few weeks, a single exploding star can outshine the entire galaxy it lives in. But the supernova, for all its spectacle, is not the main character in this story. The main character is what it leaves behind. Sitting at the center of the expanding debris cloud, still glowing at temperatures of 10 billion degrees, spinning at extraordinary speed, is the neutron star. It is roughly 20 kilometers wide. It contains between 1.4 and 2.1 times the mass of the Sun. Its surface gravity is about 2 billion times what you feel standing on the Earth right now, which means that if you could somehow place a coin on its surface, that coin would hit with the energy of a small nuclear weapon. The neutron star's crust, yes, it has a crust, a rigid shell of crystallized iron and exotic nuclei, is the hardest material in the universe, and it would need to be because the forces acting on it are beyond anything that exists anywhere else in nature, and it is magnetic. Every star has a magnetic field, and when that star collapses from something 1,000,000 kilometers wide to something 20 kilometers wide, the field does not disappear. It is compressed along with everything else. The same principle that makes a figure skater spin faster when she pulls her arms in applies here, except instead of arms, it is an entire stellar magnetic field, and instead of pulling in a little, it is being crushed by a factor of roughly 50 billion. A star that had a modest magnetic field now has a neutron star with a field of around 1 trillion Gauss. 1,000,000 times stronger than the most powerful magnet ever built on Earth. That alone makes a neutron star one of the most extreme objects in existence. Pulsars, the ones that sweep beams of radio waves across the sky like cosmic lighthouses, are neutron stars, and they have been studied for decades. They are dense, fast, magnetic, and fascinating. But they are, in a sense, normal. They are what happens when stellar collapse goes according to the standard recipe. Roughly 1 in 10 times, though, the recipe changes. The newborn neutron star is spinning at exactly the right speed, at exactly the right temperature, with exactly the right initial magnetic field. And something else happens entirely. A mechanism kicks in during the first few seconds of the neutron star's life that takes an already extraordinary magnetic field and amplifies it by a factor of 1,000, pushing it to a strength that physics barely knows how to describe. That mechanism is called the dynamo, and when it works, in that narrow window of conditions, in those first chaotic seconds after the collapse, what comes out the other side is no longer an ordinary neutron star. It is a magnetar, and the magnetic field it carries is not a trillion Gauss, it is a quadrillion. The idea that some neutron stars could possess magnetic fields 1,000 times stronger than their already extreme counterparts was not an obvious one. For most of the 20th century, the physics community was perfectly comfortable with the standard picture. A massive star collapses. It produces a neutron star with a magnetic field of about 1 trillion Gauss. And that neutron star goes on to live a long, gradually slowing existence as a pulsar. The models were clean, the observations fit. There was no particular reason to suspect that nature had something else in mind. Then, in 1992, 2 theoretical physicists, Robert Duncan at the University of Texas at Austin and Christopher Thompson at the University of Toronto, asked a question that changed the field entirely. They wanted to know what would happen if the conditions inside a newly born neutron star were just right. Not for the standard outcome, but for something far more extreme. What they found, when they ran the numbers, was that under a narrow set of circumstances, the newborn neutron star could amplify its own magnetic field by a factor of roughly 1,000, pushing it from the already staggering baseline of 1 trillion Gauss to something approaching a quadrillion. They called this hypothetical object a magnetar, and when they published the paper, almost no one paid attention. The reason the physics community shrugged is understandable. In 1992, there was no direct observational evidence that such objects existed. The soft gamma repeaters, those mysterious sources that had been sporadically spitting out bursts of low-energy gamma rays since the first one was detected in 1979, were still poorly understood, and most astronomers were not particularly interested in reinterpreting 13-year-old data through the lens of an untested theory about exotic magnetic fields. Duncan and Thompson's paper was elegant, but it was speculative. It sat on the shelf for 6 years. What changed everything was the work of Cristian Cuveliotu. In May 1998, Cuveliotu, a NASA astrophysicist at the Marshall Space Flight Center, led an international team that used the Rossi X-ray Timing Explorer to measure the spin and spin-down rate of SGR 1806-20, a soft gamma repeater located on the far side of the galaxy. The spin-down rate of a neutron star is, in effect, a speedometer for its magnetic field. The stronger the field, the faster the star loses rotational energy, and the more rapidly its spin decays. When Cuveliotu's team measured the spin-down of SGR 1806-20, the number they got implied a magnetic field strength that matched Duncan and Thompson's theoretical predictions almost exactly. The magnetar was no longer hypothetical. 4 years later, Vicky Caspi and her colleagues at McGill University in Montreal found soft gamma repeater-like bursts coming from a completely different class of neutron star, the anomalous X-ray pulsars, objects that had been puzzling astronomers with their unusually bright X-ray emission for over a decade. With that discovery, the two populations merged into one. Soft gamma repeaters and anomalous X-ray pulsars were both magnetars, and the number of known examples doubled overnight from roughly 5 to about 10. That same year, Todd Strohmeyer and Ala Ibrahim at NASA's Goddard Space Flight Center captured a spectral line from SGR 1806-20 at an energy of 5 kiloelectronvolts, a measurement that was consistent down to the decimal with a proton sitting in a magnetic field of 1 quadrillion Gauss. The theoretical prediction, the spin-down measurement, and the direct spectral evidence now all pointed to the same conclusion. But knowing that magnetars exist and understanding how they are made are two different things, and the mechanism behind their creation remains one of the most fascinating open questions in stellar astrophysics. Here is what we think happens. In the final moments before a massive star collapses, its core is a seething, turbulent environment. Temperatures in the tens of billions of degrees, densities that compress matter beyond anything found elsewhere in nature, and violent convective currents that churn the collapsing material like water in a boiling pot. Every neutron star is born in this chaos, and everyone inherits some version of the parent star's magnetic field, compressed to extraordinary strength by the collapse itself. That much is standard physics, conservation of magnetic flux, the same principle that explains why a spinning figure skater accelerates when she pulls her arms inward. What Duncan and Thompson realized is that under certain conditions, this inherited field is not the end of the story, but the beginning of it. If the newborn neutron star is spinning fast enough, on the order of 1 full rotation every few milliseconds, and if its interior is hot enough and turbulent enough, then the combination of rapid rotation and violent convection can drive what physicists call a dynamo, a self-reinforcing feedback loop in which the motion of electrically conducting fluid amplifies the existing magnetic field, which in turn drives more fluid motion, which amplifies the field further. It is the same basic process that generates the Earth's magnetic field deep in its liquid iron core, and the same process that produces the Sun's magnetic cycle, except that in a newly born neutron star, the conducting fluid is not liquid iron or solar plasma, but a churning ocean of neutrons, protons, and electrons at nuclear densities, spinning at 1,000 rotations per second in a gravitational field 2 billion times stronger than the one you are sitting in right now. The dynamo has a ceiling. There is a maximum magnetic field strength it can produce before it exhausts the available rotational and thermal energy. And that ceiling, Duncan and Thompson calculated, sits at roughly 10 to the 15th Gauss, a quadrillion. That is the number. If the dynamo runs at full efficiency, it converts enough energy to push the magnetic field all the way to this theoretical maximum, and the result is a magnetar. If conditions are slightly off, the spin a little too slow, the temperature a little too low, the convection a little too weak, the dynamo either does not engage at all or produces a field that falls short of the magnetar threshold. And what you get instead is an ordinary neutron star that will go on to live a quiet life as a pulsar. The window is narrow. The best current estimates suggest that roughly 1 in every 10 core collapse supernovae produces a magnetar rather than a standard neutron star, which means that the conditions have to align within a surprisingly tight range. It is not unlike a combination lock. Every dial has to land in the right position within the first few seconds after the collapse, and if even one of them is off by a small margin, the lock does not open. The magnetar phase is not triggered. The monster is never born. But when it is, when every condition aligns and the dynamo runs to completion, what emerges from the cooling debris of the supernova is an object that carries a magnetic field strong enough to reshape the fundamental behavior of matter, radiation, and even empty space itself. The question of what that field actually does, how it reaches across distances that should be safe, and how it turns 20 kilometers of dead star into the most dangerous object in the known universe, is where the real story begins. A magnetic field is an invisible thing. You have lived your entire life inside one. The Earth generates a field of about half a Gauss, strong enough to swing a compass needle but too weak to do much else. And you have never once felt it. You could hold a refrigerator magnet in your hand at roughly 100 Gauss, and the only evidence of the field would be the gentle tug when you bring it near something metallic. Even a hospital MRI machine, which uses a magnetic field of 10,000 Gauss to see through your skin and muscle and into your bones, produces no sensation at all. You lie inside the bore of the machine and feel nothing, despite the fact that the field surrounding you is 20,000 times stronger than the one the Earth produces. The strongest magnetic field ever generated by human engineering in a controlled laboratory setting using superconducting coils and enormous amounts of electrical power is somewhere in the neighborhood of 450,000 Gauss. That is already 1,000,000 times the Earth's field, and at that intensity the magnets themselves are under such tremendous mechanical stress that engineers have to design them with explosive containment in mind, because the forces involved can tear the apparatus apart. At Los Alamos and at a weapons laboratory in Sarov, Russia, physicists have pushed further by using chemical explosives to compress a magnetic field into a smaller and smaller volume, briefly reaching fields of about 10 million Gauss. But briefly means a fraction of a millisecond before the equipment is destroyed. 10 million Gauss is the practical ceiling of human technology. Beyond that, the machines break. A magnetar's field is 100 billion times stronger than that ceiling. There is no analogy that truly communicates what 10 to the 15th Gauss means, because the human brain did not evolve to process numbers on that scale. But there are ways to make the consequences real, and the consequences are where the understanding lives. Consider what happens to an atom. Under normal conditions, the conditions you exist in right now, an atom is roughly spherical. The electron cloud surrounds the nucleus in a probabilistic haze, and the shape of that cloud determines everything about the atom's chemistry. How it bonds with other atoms, what molecules it can form, what materials it can build, what biology it can sustain. Chemistry, in the most fundamental sense, depends on atoms being approximately round. In a magnetic field of about 100 million Gauss, 10,000 Tesla, atomic orbitals begin to deform. The electrons, which are charged particles, respond to the field by aligning their motion along the field lines, and the atom stretches. It is no longer spherical. It becomes elongated, like a rugby ball, and its chemistry starts to change in subtle ways. This is already well beyond anything that exists on Earth, but it is still a regime where recognizable atomic physics applies. At 10 billion Gauss, 1,000,000 Tesla, the deformation becomes grotesque. A hydrogen atom, normally about 1 angstrom across, is squeezed to roughly 200 times narrower than its natural diameter. It is no longer a sphere or even an ellipsoid. It is a thin, rigid needle stretched along the magnetic field lines into a shape that has no equivalent in terrestrial chemistry. At this intensity, atoms cannot form normal molecular bonds. The chemistry that sustains everything you know, water, proteins, DNA, the calcium in your bones, the iron in your blood, simply does not work. It is not that biological life would struggle. It is that the concept of a molecule, as you understand it, ceases to be meaningful. And a magnetar's field is 1,000 times stronger than even this. At the full magnetar strength of 10 to the 15 Gauss, atoms are compressed into structures so narrow that they resemble one-dimensional wires more than anything you would recognize as matter. These wire-like atoms can chain together into long polymeric strands along the field lines, forming a kind of exotic material that coats the magnetar's surface, a forest of atomic needles standing upright in the magnetic field, made of matter that does not and cannot exist anywhere else. The magnetic field's energy density at this strength is about 4 times 10 to the 25 joules per cubic meter, and the mass equivalent of that energy, because Einstein's equation works here too, and energy has weight, is more than 10,000 times the density of lead. The field is so strong that it is, in a very literal sense, heavier than most solid materials. Magnetism, at this scale, has mass. This is what the numbers mean when you translate them out of scientific notation and into physical consequences. A magnetar's field does not merely attract or repel things the way a household magnet does. It restructures the fundamental architecture of matter itself. If you could somehow approach a magnetar, which you cannot, but the thought experiment is clarifying, the field would begin altering your body long before you got anywhere near the surface. At a distance of roughly 1,000 kilometers, the electron clouds of every atom in your body would be distorted beyond the point where normal chemistry can function. The molecular bonds holding your cells together would fail, not because they were pulled apart by force, but because the conditions under which those bonds can exist would no longer apply. You would not be crushed or torn or burned. You would simply stop being matter in any configuration capable of sustaining life. And here is the detail that makes this concrete in a way that no amount of physics can, at a distance of halfway from the Earth to the Moon, about 192,000 kilometers, a gap so large that you could not see the magnetar with the naked eye even if you were looking directly at it. The magnetic field would still be strong enough to wipe the data from every credit card on the planet. Every magnetic stripe, every piece of magnetically stored information erased. Not because the field is physically touching those objects, but because at that distance, it still exceeds the threshold required to disrupt the organization of magnetic domains in a thin strip of ferromagnetic material. A magnetar you could not even see would reach across empty space and quietly rearrange the information stored on objects in your wallet. The Earth's magnetic field deflects compass needles. A refrigerator magnet holds a shopping list to a door. An MRI lets doctors see inside your body. The strongest laboratory magnet ever built required a building full of equipment and lasted for a fraction of a second before it destroyed itself. A magnetar does not operate on this spectrum. It exists so far beyond it that comparison almost loses its meaning. The distance between a refrigerator magnet and a magnetar is not like the distance between a candle and a bonfire. It is like the distance between a candle and the total energy output of a star. The kind of gap where the small end of the comparison simply vanishes into irrelevance. And all of this, the atomic deformation, the chemistry breaking field strength, the credit card erasing reach, describes the magnetar at rest. When the magnetar is calm, when nothing is happening, when it is simply sitting in space and rotating once every few seconds, this is what its field does to the space around it. The question of what happens when that field is disturbed, when the magnetar's own crust cannot withstand the stress any longer and something gives way, is an entirely different order of violence. The surface of a magnetar is not what you might expect from a dead star. It is not molten, not gaseous, not a churning sea of plasma like the surface of the Sun. It is solid, a rigid crystalline shell made of iron nuclei and free electrons, compressed to densities that make steel feel like cotton wool by comparison. This crust is, by a considerable margin, the strongest material in the known universe. It has to be because it is the only thing standing between the magnetar's interior, a superfluid ocean of neutrons at nuclear density, and the vacuum of space, and the forces acting on it from below are almost beyond description. Beneath the crust, the magnetar's colossal magnetic field is not static. It evolves. Over weeks, months, sometimes years, the field lines shift and rearrange themselves as currents deep in the star's interior slowly redistribute the magnetic energy. And because the field is anchored to the crust, threaded through it, frozen into the crystalline lattice the way iron filings align on a bar magnet, every shift in the interior field pulls on the crust from below. Imagine gripping a sheet of metal at its edges and slowly twisting it. At first, the metal flexes. It bends elastically, absorbing the strain, deforming but not breaking. You can feel the resistance building in your hands, but the sheet holds. It holds because metal has a certain tolerance for deformation before something irreversible happens. A magnetar's crust has that same tolerance, and it is enormous. The sheer strength of nuclear matter operating under pressures that do not exist anywhere else in the universe. For a long time, the crust accommodates the changing magnetic field beneath it. It bends, it flexes, it absorbs the accumulating strain the way a bridge absorbs the weight of traffic, distributing the stress across its structure, holding firm. But the magnetic field keeps evolving, and the stress keeps building, and there is a limit, a precise physical limit, beyond which the crystalline lattice cannot deform any further without fracturing. When that limit is reached, the crust breaks. The fracture propagates at a significant fraction of the speed of light. Not at the speed of sound, the way an earthquake rupture travels through rock on Earth, but at a velocity so extreme that the entire failure is over before a human brain could register a single nerve impulse. Data from the European Space Agency's cluster and double star satellites analyzing the December 2004 event estimated that the fracture in SGR 1806-20's crust was roughly 5 kilometers across, a quarter of the magnetar's total diameter. Picture a crack running across a quarter of a planet's surface, opening and closing in a fraction of a millisecond, releasing all the elastic energy that had been building in the crust for months or years in one catastrophic instant. The energy released by this fracture on its own would already be extraordinary. But the fracture is only the trigger. What follows is far worse. When the crust breaks, the footpoints of the magnetic field lines, the places where those lines are anchored into the solid surface, suddenly shift. Field lines that had been slowly accumulating tension are abruptly displaced, and the magnetic structure above the surface, the magnetosphere that extends thousands of kilometers into space, is thrown into violent instability. What happens then is a process called magnetic reconnection. Opposing field lines collide, annihilate, and release their stored energy as radiation, heat, and accelerated particles. It is the same mechanism that produces solar flares on our sun, where tangled magnetic loops above sunspots occasionally snap and reconnect, sending bursts of charged particles streaming toward the Earth. The physics is identical. The scale is not. A large solar flare releases about 10 to the 25 joules of energy. It can disrupt satellite communications, trigger auroras visible from mid-latitudes, and occasionally cause power grid failures across entire continents. These are serious events. The 1989 solar storm that knocked out the electrical grid across Quebec for 9 hours was caused by a solar flare, and it remains one of the most dramatic demonstrations of space weather's ability to reach down and touch everyday life. A solar flare is, by any terrestrial standard, a powerful event. A magnetar giant flare releases roughly 10 to the 39 joules, 100 trillion times more energy, in about a tenth of a second. If you placed a solar flare and a magnetar flare side by side and tried to compare them, the solar flare would be so small relative to its counterpart that it would essentially round to zero. Brian Gainsler of the Harvard-Smithsonian Center for Astrophysics, who studied the aftermath of the 2004 event, described it with a phrase that has stuck in the literature ever since: a super solar flare. He was not being hyperbolic, he was being conservative. The reconnection events during a magnetar flare generate electric fields so intense that they accelerate charged particles to velocities approaching the speed of light within distances shorter than a human hair. This makes a magnetar flare, for the brief duration of its existence, the most powerful particle accelerator in the universe, exceeding anything CERN has ever built or could ever build by many orders of magnitude. The accelerated particles collide with photons and with each other, producing cascades of electron-positron pairs, matter and antimatter, conjured from pure energy in quantities that would be unimaginable in any laboratory setting. These pairs form a trapped fireball of superheated plasma, confined by the magnetar's own field, radiating X-rays and gamma rays at luminosities that can, for a fraction of a second, outshine every other star in the galaxy combined. And all of this begins with a crack in a shell of crystallized iron, 20 kilometers across, on a dead star that has been quietly accumulating stress in the dark. The comparison to earthquakes is inevitable, and it is instructive, but only up to a point. The strongest earthquake ever recorded on Earth was the 1960 Chilean event, which registered 9.5 on the Richter scale and released energy equivalent to about 25 gigatons of TNT. A magnetar starquake registers roughly 32 on the same scale. The Richter scale is logarithmic, which means each whole number represents approximately 32 times more energy than the one before it, and the gap between 9.5 and 32 represents a multiplication factor so large that writing it out in full notation would fill a line across this page. The comparison to terrestrial earthquakes is technically valid, in the sense that both involve the fracture of a rigid material under accumulated stress, but the energies involved are separated by a gulf so wide that the two phenomena share a name more out of convenience than genuine kinship. What matters though, what makes starquakes more than an academic curiosity, is that they are not one-time events. A supernova happens once and it is over. A magnetar quakes repeatedly, unpredictably, for as long as its magnetic field remains strong enough to stress the crust beyond its breaking point. Some quakes are small, producing brief bursts of X-rays that last a few milliseconds and release relatively modest amounts of energy. Others are intermediate, capable of disrupting instruments on satellites thousands of light years away. And then, perhaps once every 50 years per source, perhaps less often because we have only been watching for a few decades and the statistics are thin, a magnetar produces something genuinely extraordinary. A giant flare, an event so energetic that it can be detected and can cause measurable physical effects from the other side of the galaxy. The first time humanity witnessed such an event, it arrived without warning from a direction no one was watching, and it overwhelmed every instrument that tried to record it. It happened on March 5, 1979, and the story of that night is one of the strangest detective tales in the history of astrophysics. In the winter of 1979, two Soviet spacecraft were drifting quietly through interplanetary space. Venera 11 and Venera 12 had completed their primary mission several months earlier. Both had successfully dropped landers into the crushing atmosphere of Venus and were now in heliocentric orbit, circling the Sun on trajectories that would carry them slowly away from Earth for the rest of their operational lives. Their instruments were still running, still recording the background hum of cosmic radiation that fills the space between planets, and there was nothing in the data to suggest that anything unusual was about to happen. At approximately 10:51 Eastern Standard Time on March 5th, the radiation counters on both spacecraft jumped from a baseline of about 100 counts per second to over 200,000. The spike happened in less than a millisecond, so fast that the instruments could not resolve the onset, only record that something had arrived and that it was orders of magnitude more intense than anything in their operational history. Whatever had hit them was not a gradual swell of energy building over minutes or hours. It was instantaneous, as if someone had flipped a switch and flooded interplanetary space with gamma radiation. 11 seconds later, the same wavefront reached Helios 2, a NASA probe in its own solar orbit, and overwhelmed its detectors. Moments after that, it struck Venus, where the Pioneer Venus orbiter was still circling the planet and saturated its gamma-ray instrument as well. The wave continued inward through the solar system, reaching the Earth's neighborhood within seconds. 3 United States Department of Defense Vela satellites, military spacecraft designed to monitor nuclear detonations in space, registered the burst simultaneously, along with the Soviet Prognoz 7 satellite and the Einstein Observatory, both in Earth orbit. Before the radiation exited the solar system entirely, it was picked up one final time by the International Sun-Earth Explorer, sitting in a halo orbit at the first Lagrange point between the Earth and the Sun. In total, 9 separate spacecraft detected the event, spread across millions of kilometers of interplanetary space. No one had predicted it, no one was looking for it, and no one, in those first hours and days, had any clear idea what it was. What the scientists did have was geometry, because the wavefront had been recorded by instruments in very different locations, from Venus to the Earth to the far side of the Sun. The slight differences in arrival time at each detector could be used to triangulate the direction of the source, in much the same way that the difference in arrival time of a sound at your 2 ears allows your brain to determine where the sound came from. The calculation took time, but when the triangulation was complete, the source had been pinpointed to within about 2 arc-seconds on the sky, an extraordinary precision for a burst that had lasted only a fraction of a second. The direction pointed away from our galaxy entirely, toward a small, irregular companion galaxy called the Large Magellanic Cloud, about 160,000 light-years from Earth. The specific location within the cloud corresponded to something astronomers already knew about: the remnant of a supernova that had exploded roughly 5,000 years ago, catalogued as N49. Somewhere inside that expanding shell of debris, something had produced the most powerful burst of extrasolar gamma radiation ever recorded, 100 times more intense than any previous event in the growing catalogue of gamma-ray astronomy. And whatever it was, it appeared to be associated with a dead star. This was a problem, because dead stars were not supposed to do this. In 1979, the standard understanding of neutron stars was fairly well established. They were dense, compact, rapidly rotating objects that emitted beams of radio waves from their magnetic poles. Pulsars, observed and catalogued by the hundreds since their discovery in 1967. Pulsars were predictable. They spun down gradually, losing energy at a steady rate, and they did not, as a rule, explode. The idea that a neutron star remnant could produce a gamma-ray burst intense enough to overwhelm instruments across the entire solar system did not fit comfortably into any existing model. Over the following months, the picture grew stranger. 2 more gamma-ray sources were identified that exhibited similar behavior: repeated bursts of soft gamma radiation separated by intervals of days or weeks from fixed positions on the sky. All 3 had been discovered within months of each other, a coincidence of timing that would later prove to be exactly that. A coincidence, an accident of observational scheduling that had nothing to do with the objects themselves. Scientists called them soft gamma repeaters, SGRs, because the gamma rays they emitted were at the low energy end of the gamma ray spectrum, and because, unlike most gamma ray bursts, they repeated. The first 3 were designated SGR-0526-66, the one associated with the March 5th event, along with SGR-1806-20 and SGR-1900+14. And then, for nearly 2 decades, the trail went quiet. A 4th soft gamma repeater was not discovered until 1998. The 3 original sources continued to emit occasional bursts, but the events were modest compared to the March 5th flare, and the broader astrophysics community treated SGRs as a curiosity, an unexplained footnote in the much larger and more active field of gamma-ray burst research. A handful of theorists worked on models, but without new data and without a compelling physical mechanism, there was little consensus and less urgency. What no one knew in those long intervening years was that the answer had already been published. Duncan and Thompson's 1992 Magnetar paper had laid out the theoretical framework that would eventually explain everything: the repeated bursts, the enormous energies, the association with young supernova remnants, the peculiar spin-down rates that would later be measured. The March 5, 1979 event, which had baffled a generation of astrophysicists, was the first observed giant flare from a magnetar. The gamma radiation that had swept through the solar system and saturated 9 spacecraft was the product of a starquake on an object whose magnetic field was strong enough to crack its own surface and release, in a fraction of a second, more energy than the Sun produces in thousands of years. But in 1979, the word magnetar did not yet exist, and the object that had announced itself so dramatically to every detector in the solar system went unexplained for 13 years. The universe had sent a signal. It took humanity more than a decade to build the theoretical language needed to read it. The second signal, when it came, was not subtle either. But by the time it arrived, in the final days of December 2004, the scientific community was ready. They had the theory, the observational tools, and the vocabulary. What they were not ready for was the scale. For 25 years after the March 5th event, SGR 1806-20 was known but not understood. It had been one of the 3 original soft gamma repeaters discovered in 1979, catalogued alongside the source responsible for the March 5th flare and a third object in the constellation Aquila, and for most of those 25 years, it behaved like a temperamental but ultimately manageable patient. Periodic outbursts of soft gamma radiation, bursts lasting fractions of a second, punctuated by long stretches of relative quiet. Astronomers monitored it when they could, noted the bursts in their databases, and moved on to more pressing questions. It was an interesting object. It was not, by any obvious measure, an urgent one. The source itself sits in one of the most crowded and obscured regions of the Milky Way. The constellation Sagittarius, as seen from Earth, points directly toward the galactic center, and the line of sight to SGR 1806-20 passes through some of the densest concentrations of gas and dust in the galaxy. At a distance of roughly 42,000 light-years, on the far side of the Milky Way, nearly as far from us as it is possible for a galactic object to be, SGR 1806-20 is invisible at optical wavelengths. You cannot see it with any telescope that observes invisible light, no matter how large the mirror or how long the exposure. It reveals itself only in X-rays and gamma rays, frequencies that can penetrate the intervening dust, and even in those bands, it spent most of its known history as a faint and intermittent source. What made the location remarkable, long before anyone understood the nature of the magnetar itself, was the neighborhood. SGR 1806-20 is not alone. It sits at the core of a young stellar cluster, embedded within one of the largest star-forming regions in the galaxy, a complex known as W31 that stretches across hundreds of light-years and contains enough raw material to build thousands of new stars. The cluster around SGR 1806-20 is home to some of the most extreme stars known to exist. At least 2 carbon-rich Wolf-Rayet stars, massive, luminous objects that are burning through the final stages of their lives and shedding their outer layers in dense, stellar winds, along with 2 blue hypergiants and an object designated LBV 1806-20, a luminous blue variable that ranks among the brightest and most massive individual stars in the entire galaxy. This is not a quiet corner of the cosmos. This is the kind of environment where massive stars are born, live fast, and die violently. And it is exactly the kind of place where you would expect to find a magnetar if you went looking for one. Through the 1990s and into the early 2000s, as the magnetar hypothesis gained traction and the observational evidence accumulated, SGR 1806-20 gradually revealed more of itself. Cuveliotu's 1998 spin-down measurements confirmed the extreme magnetic field. The spectral line detected by Strohmeyer and Ibrahim in 2002 pinned the field strength to a quadrillion Gauss with direct observational evidence. By the middle of 2004, SGR 1806-20 was recognized as one of the most highly magnetized objects ever observed, possibly the most magnetized, and its rotation had been precisely timed at one full turn every 7.56 seconds, making it a slow spinner even by magnetar standards. Its original rapid rotation long since bled away by the breaking force of its own colossal field. And in the summer of 2004, SGR 1806-20 began to stir. Starting in mid-year, the source entered an active phase. The frequency and intensity of its X-ray bursts increased noticeably, a pattern that had been seen before in other magnetars and that is generally interpreted as a sign of mounting stress in the crust, the magnetic field evolving beneath the surface, pulling on the crystalline lattice, building towards something. Astronomers noted the uptick, papers were written, monitoring campaigns were adjusted to capture more data. There was professional interest, certainly, but no particular alarm. Magnetars entered active phases regularly. Most of them settled down after a few months without producing anything extraordinary. There was no reason to believe SGR 1806-20 would be different. On the evening of December 27, 2004, 2 days after Christmas, during the week when much of the astronomical community was on holiday, SGR 1806-20 proved that assumption wrong in the most emphatic way possible. The light that arrived that night had left the magnetar 42,000 years earlier, roughly the time when anatomically modern humans were first arriving in Europe, when the Neanderthals were in their final decline, when the ice sheets of the last glacial maximum had not yet reached their fullest extent. For 42,000 years, that burst of radiation had been crossing the galaxy at the speed of light, threading its way through the spiral arms, passing through molecular clouds and stellar nurseries and the vast empty stretches between them, completely undiminished and perfectly indifferent to everything in its path. And when it finally reached the inner solar system and washed over the small rocky planet third from the Sun, it carried with it more energy than any event of its kind ever recorded. 100 times more powerful than the March 5, 1979 flare that had overwhelmed 9 spacecraft and launched an entirely new branch of astrophysics. The instruments were better in 2004 than they had been in 1979. There were more of them, they were more sensitive, and they were specifically designed to capture exactly this kind of event. None of it mattered. The burst was so far beyond the design parameters of every gamma-ray detector in orbit that the initial spike, the first 200 milliseconds, the part that contained the most critical information about the energetics of the event, was lost to saturation in nearly every instrument that tried to record it. Integral went blind for 0.7 of a second. Swift's Burst Alert telescope, which had been launched just months earlier and represented the most advanced gamma-ray detection technology available, was overwhelmed instantly. Detectors that had been built to stare into the heart of the most violent explosions in the universe were forced to look away. What they did manage to capture, once the initial spike had passed and the instruments recovered, was a pulsating tail of radiation that lasted more than 6 minutes, modulated at the magnetar's known rotation period of 7.56 seconds. the signature of a hot plasma fireball trapped by the magnetic field, spinning with the star and slowly cooling. The tail alone, the afterglow of the main event, carried enough energy to rank among the most powerful bursts ever observed from any soft gamma repeater. It was the equivalent of watching the embers of a fire and realizing that those embers, on their own, were brighter than anything else in the sky. The full accounting came later as data from multiple satellites was collated and cross-referenced, and the physics was worked through. The total isotropic energy of the flare was calculated at 2 × 10⁻46 ergs, a number so large that it requires context to mean anything at all. In the 1/5 of a second that the initial spike lasted, the magnetar had released as much energy as the Sun radiates in 250,000 years. For that brief fraction of a moment, a single neutron star 20 kilometers across had outshone the full moon in gamma rays from the other side of the galaxy. The event was, at the time, the brightest extrasolar transient ever recorded in any wavelength, and it remains one of the most energetic astrophysical phenomena ever directly observed. The implications arrived in waves. The first was immediate and practical. If this event had occurred not at 42,000 light-years, but at 40 megaparsecs, still within the local group of galaxies, but far enough to be extragalactic, it would have been indistinguishable from a short, hard gamma-ray burst. This meant that some fraction of the short gamma-ray bursts that had been detected over the years from distant galaxies might not be neutron star mergers or collapsing stars at all. They might be magnetar flares, misidentified because of distance. A single observation had potentially reclassified an entire subpopulation of cosmic explosions. The second implication was more personal. If a flare of this magnitude had originated from a magnetar within 10 light-years of the Earth, comfortably inside the Sun's galactic neighborhood, a distance that contains several dozen known stars, the gamma radiation would have been intense enough to destroy a significant fraction of the ozone layer and trigger a mass extinction event comparable in severity to a nearby supernova. The nearest known magnetar, 1E1048.1-5937 in the constellation Carina, is about 9,000 light-years away, which offers a reasonable margin of safety. But the December 27th event was a reminder that reasonable margins are a human concept, and the universe does not read the papers. Victoria Caspi of McGill University, who won the 2004 Hertzberg Medal for her work on magnetars, put it plainly in the years that followed. Magnetars are the only deep space objects that have directly, measurably, physically affected the Earth. Not through tidal forces, not through slow gravitational perturbation over millions of years, but through a single event lasting less than a second from 50,000 light-years away. No other class of object in the known universe has done this. The fishermen in the Arctic who saw the aurora that night did not know what had caused it. The gamma-ray astronomers who spent the following weeks reconstructing the light curve did not sleep much. And the magnetar itself, 20 kilometers across, 42,000 light-years distant, continued to rotate once every 7.56 seconds, indifferent to the fact that it had just delivered the most powerful signal any instrument on or near the Earth had ever received from beyond the solar system. But the December 27th event was not the end of what magnetars had to teach us. It was not even the most unsettling part of the story, because the question that lingered after the data had been analyzed, the papers published, and the awards given was not about what had happened 50,000 light-years away. It was about what would happen if the distance were shorter. And the answer to that question is the reason magnetars hold the title they hold. Imagine you are falling toward a magnetar. Not quickly. There is no rush. You are approaching from a great distance, drifting inward through empty space, and the magnetar is so small and so far away that you cannot see it yet. At this range, it is indistinguishable from any other faint point source in the sky, lost among the background stars, radiating a dim glow of X-rays that only a space telescope could detect. Nothing about the view suggests danger. The space around you feels ordinary, cold, dark, silent, and if you did not know what was waiting ahead, you would have no reason to suspect that anything about this particular patch of the galaxy was different from any other. At a distance of about 192,000 kilometers, roughly half the distance from the Earth to the Moon, the first sign arrives, though you would not feel it. At this range, the magnetar's field strength, falling off with the cube of the distance, has diminished from its surface value of a quadrillion Gauss to something far weaker, but still far stronger than any magnetic field human civilization has ever encountered at close range. If you were carrying a credit card, the magnetic stripe on its back, that thin band of ferromagnetic material encoding your account number and expiration date, would already be scrambled beyond recovery. Every piece of magnetically stored data within range would be wiped clean, not through physical contact, not through heat or pressure, but through the quiet rearrangement of magnetic domains in materials that were never designed to encounter a field of this intensity. At half the Earth-Moon distance, a magnetar you could not see with the naked eye would have already reached into your pocket and erased your financial identity. This is not the dangerous part. Continue inward. The magnetar is still invisible to the unaided eye. 20 kilometers is far too small to resolve at these distances, but its presence is becoming increasingly difficult to ignore. Electronic equipment begins to malfunction. Semiconductor circuits, which depend on the precise behavior of electrons moving through carefully doped silicon, are disrupted by the growing field. Navigation instruments give nonsensical readings. Communication systems fail. The magnetic field at this range is not strong enough to physically damage the structure of your spacecraft, but it is strong enough to render every piece of sophisticated technology aboard it useless. You are, in a functional sense, blind and deaf, drifting towards something you cannot see on instruments that no longer work. At roughly 3,000 kilometers, a distance that in terrestrial terms is comparable to the span from London to Moscow, the field crosses a threshold that moves the danger from technological to biological. At this range, the magnetic field is strong enough to significantly distort the electron orbitals of atoms, not by a subtle amount, not in a way that a sensitive instrument might detect, but a human body might tolerate. The distortion is gross, structural, and immediate. The atoms in your body, every carbon atom in your muscles, every calcium atom in your bones, every iron atom in your hemoglobin, begin to deform, stretching along the field lines into elongated shapes that cannot participate in normal chemical bonding. The molecular architecture that holds your cells together starts to come apart, not because a force is pulling it apart, but because the geometry of the atoms themselves has changed so fundamentally that the bonds can no longer form. You would not feel pain exactly because pain requires functioning nerves, and your nerves rely on the same molecular chemistry that is ceasing to exist. The transition from living organism to dissociated matter would be rapid and, in a clinical sense, total. At 1,000 kilometers, the field strength reaches a level where the chemistry of life is not merely disrupted, but categorically impossible. No carbon-based molecular structure can maintain its integrity. No protein can fold. No membrane can hold. The concept of biology becomes inapplicable, not because the environment is hostile to life in the way that the vacuum of space is hostile, or the way that extreme heat is hostile, but because the physical substrate on which life depends has been restructured at the atomic level into something that cannot support it. You are not killed by the magnetar. You are unmade by it. And you are still 1,000 kilometers from the surface. This progression, from data erasure to electronic failure, to molecular destruction to atomic deformation, unfolds across distances that, by astronomical standards, are trivially small. The entire kill zone of a magnetar's static magnetic field, from the point where your credit cards fail to the point where your atoms lose their shape, fits comfortably within the Earth-Moon system. In the context of interstellar distances, it is a pinprick. You would have to be extraordinarily unlucky or extraordinarily foolish to wander into it. But the static field is only half of the threat, and it is not the half that keeps astrophysicists awake at night. A magnetar's magnetic field at rest is a local hazard. Terrible, certainly, but confined to a small region of space that nothing is likely to blunder into by accident. The December 27th event demonstrated something fundamentally different, that a magnetar during a giant flare can project lethal force across interstellar distances. The gamma radiation from SGR 1806-20 physically altered the Earth's atmosphere from 50,000 light-years away. That was the actual distance. That was the real measurement. And when scientists calculated what a comparable event would do at closer range, the numbers stopped being academic and became, in a word, existential. At 10 light-years, a distance that contains roughly a dozen known star systems from the Sun's current position, a giant flare on the scale of the December 27th event would deliver enough gamma radiation to destroy between 30 and 50% of the Earth's ozone layer in a matter of seconds. The ozone layer is what stands between every living thing on the surface of this planet and the full intensity of the Sun's ultraviolet radiation. Lose half of it, and the surface UV flux increases to levels that cause widespread cellular damage in exposed organisms, disrupt photosynthesis in plants and phytoplankton, collapse marine food chains that depend on surface-dwelling microorganisms, and trigger a cascade of ecological failures that, in geological terms, constitutes a mass extinction. This is not speculation. The ozone depletion pathway is well understood from studies of nuclear weapons effects and volcanic eruptions, and the energy delivered by a magnetar flare at 10 light-years exceeds the relevant thresholds by a comfortable margin. Brian Gaensler's widely quoted assessment that a December 27th scale event within 10 light-years would have severely damaged the atmosphere and potentially triggered a mass extinction was not a dramatic flourish for the press. It was a straightforward reading of the physics. The honest question then is whether this could happen. And the honest answer is that it almost certainly has somewhere in the galaxy at some point in the past 4 billion years, though whether it has happened to Earth specifically is unknown and may be unknowable. The nearest confirmed magnetar, 1E1048.1-5937, is 9,000 light-years away in the southern constellation Carina, which places it well outside the danger radius. But the catalogue of known magnetars is a catalogue of the ones we have detected, which is a very different thing from a catalogue of the ones that exist. As of 2021, only about 30 magnetars have been confirmed in the Milky Way, but theoretical estimates suggest there may be more than 1 million, most of them long since faded into quiescence, their magnetic fields decayed below the threshold of detectability, drifting unseen through the galactic disk. There is a particular detail about this that deserves attention. In 2008, astronomers discovered a new magnetar designated SGR 0501+4516, located only 15,000 light-years away. It had escaped detection until then because it had been essentially dark, emitting so little radiation during its quiescent phase that no existing survey had picked it up. It was found only because it entered an active phase and began producing bursts. Phil Plait, the astronomer and science writer who covered the discovery for Discover magazine, noted with characteristic understatement that one of his main reasons for feeling entirely safe from magnetar threats, the assumption that we had already detected all the nearby ones, had been somewhat eroded. If a magnetar could hide at 15,000 light-years, the question of what might be hiding at 5,000 or 1,000 was no longer entirely comfortable. The truth is that we do not know how many magnetars are close enough to pose a genuine threat, because we do not know how many magnetars are close. We know the ones that are active, the ones that are emitting, the ones that have announced themselves through bursts and flares. The quiet ones, the ones in the long intervals between outbursts, the ones whose fields have decayed just enough to stop producing detectable radiation, but not enough to prevent one final catastrophic flare, remain invisible. They are out there, presumably in numbers that dwarf the known population, distributed through the galaxy according to the same patterns that govern the distribution of massive stars and their remnants. And that is the argument for the title. Not that a magnetar will reach out and destroy the Earth tomorrow. The probability of that, in any given century, is vanishingly small. But that among all the objects the universe has produced, the magnetar is the one that combines the greatest destructive reach with the greatest unpredictability. A black hole is more massive, but it cannot hurt you from a distance. A supernova is more energetic, but it happens once and it is over. A gamma-ray burst is more focused, but it requires the death of a star to produce. A magnetar sits quietly in space, undetectable during its quiescent phases, and then, without warning, cracks its own surface and delivers a pulse of energy that can be measured from the other side of the galaxy. It does this repeatedly, over a lifetime of 10,000 years, and no one can predict when the next one will come. That combination, power, reach, repetition, and unpredictability, is what makes the magnetar the most dangerous object in the universe. Not the most massive, not the most energetic, not the most exotic, the most dangerous. The distinction matters, and it is a distinction that belongs to no other object we have found. But there is a quality that belongs to magnetars that goes beyond danger, a quality that makes them not just frightening but genuinely strange in a way that touches the foundations of physics. Because the magnetic field of a magnetar does not only reshape matter, it reshapes the vacuum itself, turning empty space into something that behaves like a physical medium, with optical properties that should not exist outside of a theoretical equation. The effect was predicted in 1936, and for 80 years, no one could find evidence that it was real. In 1936, two physicists in Germany published a paper that almost no one read. Werner Heisenberg, already famous, already the architect of the uncertainty principle that bears his name, and his doctoral student Hans Heinrich Euler had been working through the mathematics of quantum electrodynamics, the theory that describes how light and charged particles interact at the subatomic level, and they had arrived at a prediction that seemed, at the time, purely academic. Their equations showed that in the presence of a sufficiently powerful magnetic field, the vacuum of space, the void, the absence of matter, the nothing between things, would begin to behave as though it were a physical substance. Specifically, it would develop optical properties. Light passing through a strongly magnetized vacuum would split into two components traveling at slightly different speeds, each with a different polarization, in exactly the same way that light splits when it passes through a birefringent crystal like calcite. They called the effect vacuum birefringence, and they knew, even as they published it, that proving it experimentally was essentially impossible. The magnetic field required to produce a measurable effect was somewhere in the vicinity of 4 × 10⁻13 Gauss, billions of times stronger than anything a laboratory could generate, then or now. The prediction was mathematically sound, physically coherent, and completely untestable. It went into the literature and stayed there for 80 years. The reason the prediction resisted experimental verification is worth understanding because it reveals something fundamental about the nature of empty space as quantum mechanics describes it. In classical physics, the physics of Newton and Maxwell, the physics that governs everything you can see and touch in daily life, a vacuum is exactly what it sounds like. Nothing. An absence. Space with nothing in it. Light moves through it at a constant speed, unaffected by anything because there is nothing there to affect it. But quantum electrodynamics tells a different story. In QED, the vacuum is not empty. It seethes with activity, a constant, undetectable froth of virtual particles, electron-positron pairs flickering into existence and annihilating each other so quickly that they cannot be directly observed, borrowing energy from the vacuum for timescales so brief that the uncertainty principle permits the transaction. Under normal conditions, this quantum foam has no measurable effect on anything. The virtual particles cancel out, the vacuum behaves as though it were empty, and classical physics works perfectly well as a description of reality. But Heisenberg and Euler's calculation showed that in an extremely strong magnetic field, the virtual particles stop being invisible. The field interacts with the fleeting electron-positron pairs, aligning and organizing them in a way that gives the vacuum itself a kind of structure, a directionality, an asymmetry that was not there before. Light passing through this structured vacuum encounters something that behaves like a medium, and different polarization states of that light interact with the medium differently, traveling at slightly different speeds. The vacuum, in effect, becomes a prism. Not a prism made of glass or crystal, but a prism made of nothing, of organized nothingness, shaped by a magnetic field into something that has measurable optical properties. For 80 years, this remained one of the most elegant and frustrating predictions in all of physics. Elegant because the mathematics was clean and the logic was airtight. Frustrating because the magnetic fields required to observe the effect were so far beyond anything achievable in a laboratory that there was no realistic prospect of ever testing it. The PVLAS experiment in Italy, a dedicated, decades-long effort to detect vacuum birefringence using the strongest available laboratory magnets and the most sensitive optical equipment, spent 25 years pushing toward the QED prediction, and, as of the most recent published results, has come close but has not yet reached the required sensitivity. The effect, if it exists at the field strengths available on Earth, is simply too small to measure with current technology. What changed was not the technology. What changed was the realization that the universe had been running the experiment all along, at field strengths no laboratory could ever approach, in a setting that was, with sufficient ingenuity, observable from 400 light-years away. In 2016, a team led by Roberto Mignani of the Italian National Institute for Astrophysics pointed the European Southern Observatory's Very Large Telescope in Chile at one of the faintest objects ever targeted for optical polarimetry, RxJ 185 6.5-3754, an isolated neutron star roughly 400 light-years from Earth. It is a member of a small group of nearby neutron stars known informally as the Magnificent Seven, radio-quiet objects that emit thermal radiation from their surfaces and possess magnetic fields in the range of 10 to the 13 Gauss, strong enough to enter the regime where Heisenberg and Euler's prediction should begin to produce detectable effects. RxJ 185 6.5-3754 is extraordinarily dim. Visual magnitude 25.5, which is about 40 million times fainter than the faintest star visible to the naked eye, and measuring its polarization required pushing the VLT to the absolute limit of its capabilities. The observation was, as Vincenzo Testa of INAF Rome described it, the faintest object for which polarization had ever been measured. What Mignani's team found was a degree of linear polarization of 16.43%, plus or minus about 5%. The number matters because when they fed it into theoretical models of neutron star emission, models that accounted for the star's temperature, its magnetic field geometry, and the expected polarization from its surface, they found that the observed degree of polarization could not be reproduced without including vacuum birefringence in the calculations. Models that left out the QED effect consistently predicted lower polarization. Models that included it matched the observation. The vacuum around this neutron star was behaving exactly as Heisenberg and Euler had predicted 80 years earlier, polarizing the light that passed through it, acting as a prism made of magnetized nothing. The result was suggestive rather than definitive, a single measurement on a single object, with error bars that left room for alternative interpretations. But it was the first observational evidence of any kind, and it came from a neutron star whose magnetic field was still 100 times weaker than a magnetar's. The implication was clear. If vacuum birefringence was detectable at 10 to the 13 Gauss, the effect at magnetar field strengths of 10 to the 15 Gauss would be not just present, but dominant, a major factor in how radiation propagates through and escapes from the magnetar's immediate environment. That implication was confirmed in dramatic fashion by NASA's Imaging X-ray Polarimetry Explorer, launched in December 2021. IXPE was the first space telescope specifically designed to measure the polarization of X-ray light from cosmic sources, and among its early targets were several known magnetars. The results, published over the following years, showed polarization degrees ranging from 15 to 80% across the magnetar sample, values so high that they could not be explained by any emission model that did not include vacuum birefringence as a fundamental component. The X-ray light escaping from these magnetars was being shaped, filtered, and polarized by the structured vacuum around them, and the degree of that shaping was consistent with QED predictions in the strong field regime. 8 decades after Heisenberg and Euler wrote down their equations, the evidence had arrived from exactly the kind of source they could never have imagined, a class of object that would not even be theorized for another 56 years after their paper was published. What this means, in plain language, is that a magnetar's influence extends beyond matter. It reaches into the fabric of space itself and changes the rules. The vacuum near a magnetar is not the same vacuum that exists between the stars or in the empty space of this room. It is a different kind of emptiness, polarized, structured, birefringent, in which photons do not simply pass through unimpeded, but are bent, split, and reorganized by a field that has turned nothing into something. At the highest field strengths, near the magnetar's surface, the QED effects become even more exotic. X-ray photons can split into pairs, or pairs can merge into single photons, and the vacuum develops a refractive index that varies with direction in a way that has no parallel in any terrestrial material. This is a magnetar's deepest strangeness, and it is the quality that separates it from every other extreme object in the universe. Black holes warp space-time. Neutron stars compress matter. But a magnetar does something that neither of those objects can do. It alters the quantum structure of the vacuum, transforming empty space into an active participant in the physics of its own environment. The void around a magnetar is not a passive backdrop. It is an instrument, shaped and tuned by the magnetic field, and it plays a role in every photon that escapes, every burst that propagates, every signal that reaches our telescopes from across the galaxy. And in April 2020, one of those signals brought with it the answer to a mystery that had been building for over a decade. A mystery involving brief, impossibly bright flashes of radio energy arriving from the distant universe, with no clear explanation and no confirmed source. The signal came from a magnetar 30,000 light-years away, and when it was identified, it did not just resolve a question. It opened an entirely new chapter in our understanding of what these objects are capable of. In 2007, an astronomer named Duncan Lorimer was sifting through archival data from the Parkes Radio Telescope in Australia when he found something that should not have been there. Buried in observations recorded 6 years earlier, in a survey that had been searching for pulsars, was a single burst of radio energy that lasted about 5 milliseconds and carried a dispersion signature indicating that it had originated far outside the Milky Way, possibly billions of light years away. The burst was extraordinarily bright for something at that distance, implying an energy release that dwarfed anything known to come from a radio source on millisecond timescales. Lorimer published the discovery, the community took note, and then spent the better part of a decade arguing about whether it was real. It was real. Over the following years, more bursts turned up in archival data, in new surveys, in observations from radio telescopes on several continents, and each one shared the same basic characteristics, a few milliseconds long, dispersed by passage through intergalactic plasma, and carrying enough energy to suggest a source that was compact, cataclysmic, and located at cosmological distances. They were named fast radio bursts, or FRBs, and by the mid-2000s, they had become one of the most actively debated topics in astrophysics. Dozens of theories were proposed to explain them: colliding neutron stars, evaporating black holes, cosmic strings, alien transmitters. The proposals ranged from the conservative to the exotic to the frankly speculative, and the reason the field could not settle on an answer was simple. No one had ever caught a fast radio burst in the act of happening. They appeared without warning, lasted a few milliseconds, and vanished, leaving behind a dispersion measure and a rough position on the sky, but nothing else. No afterglow, no counterpart at other wavelengths, no smoking gun. The breakthrough, when it came, did not arrive from a distant galaxy. It arrived from inside the Milky Way, from an object that astronomers had been watching for years without suspecting it had anything to do with fast radio bursts at all. SGR 1935+2154 is a magnetar in the constellation Vulpecula, about 30,000 light-years from Earth. It was first identified in 2014 by the Neil Gehrels Swift Observatory during a routine burst of X-ray activity, catalogued as a soft gamma repeater, and added to the small but growing roster of confirmed magnetars. For most of the following 6 years, it behaved unremarkably. Occasional X-ray bursts, periods of activity followed by periods of quiet, the standard pattern of a magnetar going about its business. It was not considered a particularly notable source. It was, by magnetar standards, ordinary. On April 27, 2020, that changed. Swift's Burst Alert telescope detected multiple bursts of gamma rays and X-rays from the direction of SGR 1935+2154, signaling that the magnetar had entered a heightened state of activity. The Fermi Gamma Ray Space Telescope independently confirmed the flaring. Alerts went out to the astronomical community, and telescopes around the world began redirecting their attention toward Vulpecula. By the following day, when that patch of sky came into view for ground-based radio telescopes in the Western Hemisphere, 2 instruments were listening. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, is a radio telescope in Penticton, British Columbia, that was originally designed to study the large-scale structure of the universe by mapping the distribution of hydrogen gas. It was not built to detect fast radio bursts, but its wide field of view and continuous operation made it an unexpectedly powerful FRB detector, and by 2020 it had become one of the primary instruments in the field. On April 28th, CHIME detected a pair of millisecond duration radio bursts from the direction of SGR 1935+2154. bursts that, in their duration, their dispersion, and their spectral characteristics, were consistent with the fast radio bursts that had been arriving from cosmological distances for over a decade. Independently and simultaneously, the Stare-2 array, a small network of radio antennas in the southwestern United States, specifically designed to detect bright radio transients within the Milky Way, recorded the same event. The Stare-2 measurement was critical because it established the fluence of the burst at over 1.5 million Jansky milliseconds, a value that placed the event squarely in the energy range of extragalactic fast radio bursts. If you took this signal and moved it to the distance of the nearest known FRB, it would still have been detectable. The radio burst from SGR 1935 plus 2154 was not merely similar to a fast radio burst. By every measurable criterion, it was one. Within hours, the space-based instruments weighed in. Integral, Conus Wind, InSight HXMT, and Agile all reported the detection of an X-ray burst from SGR 1935 plus 2154 that was coincident, both spatially and temporally, with the radio event. The X-ray burst had a distinctive double-peaked structure separated by about 29 milliseconds, a spectrum harder than the typical magnetar burst, and an energy that, while modest by giant flare standards, was far beyond anything associated with normal magnetar activity. The radio and X-ray emissions had occurred at the same time, from the same location, produced by the same physical event inside the magnetosphere of a known magnetar. The event was designated FRB 200428, and it resolved, in a single observation, a question that had consumed the field for 13 years. Magnetars could produce fast radio bursts. The connection was no longer theoretical, no longer circumstantial, no longer a matter of modeling and inference. It was a direct detection. The first fast radio burst ever observed from within the Milky Way, and the first ever traced to a known source. The energy of FRB 200428 was roughly 4,000 times greater than the most powerful radio pulse ever recorded from the Crab pulsar, which had previously held the record for the brightest galactic radio transient on millisecond timescales. And yet, by the standards of the extragalactic FRB population, it was comparatively modest, about 30 times weaker than the faintest fast radio burst detected from beyond the galaxy. This gap in energy was significant because it suggested that FRB 200428 sat near the low end of a much broader distribution, and that the full-strength events arriving from billions of light-years away might represent far more violent episodes from far more powerful magnetars. The galactic burst was a whisper from a nearby source. The extragalactic ones were screams from sources so distant that only the loudest could be heard. What made the discovery particularly striking was what did not happen in the days surrounding it. The 500-meter aperture spherical telescope in China, FAST, the largest single-dish radio telescope on Earth, had been monitoring SGR 1935 plus 2154 during the same active period and had observed 29 separate X-ray bursts from the magnetar in the days before FRB 200428. Not one of those bursts was accompanied by a detectable fast radio burst. The magnetar had been flaring repeatedly, producing X-ray emissions at a steady clip, and the radio sky had remained silent through all of it, until, for reasons that remain poorly understood, a single burst broke through. Bing Zhang of the University of Nevada, Las Vegas, noted that this non-detection was itself scientifically important because it demonstrated that the conditions required to produce a fast radio burst were not easily satisfied. A magnetar does not produce an FRB every time it flares. The radio emission appears to require something specific, a particular configuration of the magnetic field, a particular angle of emission, a particular combination of physical conditions within the magnetosphere. And that specificity is why FRBs from magnetars are rare, even when the magnetar itself is active. The full picture, as it stands today, is still incomplete. FRB 200428 established that magnetars can produce fast radio bursts, but whether magnetars are responsible for all FRBs, including the repeating sources that have been localized to specific galaxies at cosmological distances, remains an open question. Some repeating FRBs show properties that are difficult to reconcile with the standard magnetar model, suggesting that additional mechanisms or more exotic magnetar configurations may be involved. The field is young, the data is accumulating rapidly, and the theoretical landscape is shifting with every new detection. But the core finding is secure, and it adds a dimension to the magnetar story that was not present before 2020. These objects do not only produce gamma rays that can blind satellites from across the galaxy, they do not only generate magnetic fields that restructure matter and polarize empty space, they also produce radio signals powerful enough to be detected from the other side of the observable universe, millisecond duration pulses of coherent radio emission that arrive without warning and vanish without trace, carrying with them information about the most extreme magnetic environments in existence. A magnetar can reach across the galaxy with gamma rays, across the solar system with its static field, and across the visible universe with its radio bursts. No other single class of object has this range, and all of it, the flares, the field, the radio pulses, the restructured vacuum, operates on borrowed time. Because a magnetar's magnetic field, the source of everything that makes it extraordinary and everything that makes it dangerous, is not permanent. It is decaying steadily and irreversibly from the moment the magnetar is born, and the clock it runs on is measured not in billions of years, like a star, or in trillions, like a black hole, but in thousands. 10,000 years, give or take. And then the most dangerous object in the universe goes quiet. The most dangerous object in the universe is dying from the moment it is born. This is not a poetic observation. It is a statement of physics. The magnetic field that makes a magnetar what it is, the field that deforms atoms, polarizes the vacuum, cracks the crust, and sends bursts of radiation across the galaxy, is not self-sustaining. It is not fed by nuclear fusion, the way a star's luminosity is fed. It is not replenished by accretion, the way a black hole's gravitational influence grows when it consumes matter. The magnetar's field is a reservoir filled once during the first seconds of the neutron star's life by the dynamo mechanism, and then drained steadily and irreversibly for every second that follows. The magnetar does not burn fuel. It spends inheritance. The processes that drain the field are slow by human standards, but catastrophically fast by cosmic ones, and they operate through three distinct mechanisms, each dominant at different depths within the star and at different stages of its evolution. In the crust, that rigid crystalline shell where starquakes originate, the dominant process is a combination of ohmic decay and a phenomenon called Hall drift. Ohmic decay is the simplest to understand. The crust, despite being an extraordinarily good conductor by terrestrial standards, is not a perfect one, and the electrical currents that sustain the magnetic field gradually lose energy to resistive heating, the same way a current flowing through a copper wire generates waste heat. The field weakens, the crust warms, and the magnetic energy is converted, watt by watt, into thermal radiation that the magnetar emits as a faint glow of X-rays. Hall drift is more subtle. It does not directly dissipate energy, but instead rearranges the magnetic field within the crust, shuffling its structure, creating smaller-scale features and sharper gradients that accelerate the ohmic losses. The two processes work in concert, the Hall drift stirring and the ohmic decay draining, and together They are responsible for much of the field evolution that drives the magnetar's surface activity during its youth. Deeper in the star, in the liquid core where neutrons exist in a superfluid state and protons may form a superconducting phase, the dominant mechanism is ambipolar diffusion, a process in which the charged particles, protons and electrons, drift relative to the uncharged neutrons under the influence of the magnetic field, carrying the field with them as they move and dissipating its energy through collisions with the surrounding neutron fluid. Ambipolar diffusion is the heavyweight of magnetar field decay. At field strengths of 10 to the 15 Gauss, the diffusion timescale drops into the range of 10,000 to 100,000 years, precisely the range that matches the observed lifetimes of active magnetars. Thomson and Duncan recognized this in their original work. The quadratic scaling of ambipolar drift velocity with field strength meant that the strongest fields decayed the fastest, which was both the mechanism that powered the magnetar's extraordinary emissions and the clock that guaranteed those emissions would eventually stop. The result is a lifespan measured in thousands of years rather than millions or billions. For context, the Sun has been burning for 4.5 billion years and will continue for roughly 5 billion more. A white dwarf, the remnant of a Sun-like star, will take trillions of years to cool to invisibility, longer than the current age of the universe. Even an ordinary neutron star, stripped of its magnetar strength field, will persist as a detectable radio pulsar for tens of millions of years before its spin decays below the threshold of emission. A magnetar's active phase, by contrast, lasts about 10,000 years. If you compressed the entire history of the universe into a single calendar year, a magnetar's active lifetime would occupy less than 2/100ths of a second on December 31st. It is, by any cosmic measure, a momentary fury, and we have seen what that fury looks like at the very beginning. On March 12, 2020, the Swift Burst Alert telescope detected a hard X-ray burst from a previously unknown source in the constellation Sagittarius, about 21,000 light-years from Earth. Follow-up observations with NICER, the X-ray timing instrument aboard the International Space Station, confirmed pulsations with a period of 1.36 seconds, making this the fastest spinning magnetar ever discovered. The source was designated Swift J 1818.0-1607, and when astronomers calculated its characteristic age from the rate at which its spin was slowing, the number they got was approximately 240 years. 240 years. This magnetar had been born roughly around the time of the American Revolution, when the light that announced its creation began its 21,000-year journey toward our telescopes. Swift J 1818.0-1607 is not just young. It is, as of its discovery, the youngest neutron star of any kind ever confirmed, and its youth makes it invaluable because it offers a glimpse of a magnetar's earliest years, the period of maximum field strength and maximum violence, before the decay processes have had time to significantly diminish the magnetic reservoir. At a field strength of about 3 × 10 to the 14 Gauss, it is already one of the most highly magnetized objects known, and its spin-down behavior shows dramatic instabilities, the rotational frequency derivative oscillating wildly before gradually converging on a mean value that suggest its magnetosphere is in a state of active, turbulent evolution. It was also detected at radio wavelengths within a week of its X-ray discovery, making it only the 5th magnetar known to emit radio pulsations and reinforcing the emerging suspicion that the boundary between magnetars and radio pulsars may be less rigid than previously thought. Nanda Rea of the Institute of Space Sciences in Barcelona, who led the observational campaigns with XMM Newton and NuSTAR, described it simply: "This object is showing us an earlier time in a magnetar's life than we have ever seen before. It is the cosmic equivalent of photographing a hurricane in its first hour of formation. The structure is still raw, still organizing, still radiating the full force of its initial energy. The flip side of that observation is that most magnetars are not like Swift J 1818.0-1607. Most are older, dimmer, their fields already in decline, and as the field weakens, the magnetar changes. The starquakes become less frequent because the magnetic stress on the crust diminishes as the field decays. The X-ray luminosity drops because there is less magnetic energy being converted to heat. The gamma-ray bursts, which depend on the field being strong enough to crack the crust and drive reconnection events, gradually cease. Over the course of a few thousand years, the magnetar transitions from a violent, unpredictable source of high-energy radiation to something much quieter. Still dense, still magnetic by any normal standard, still rotating, but no longer active in any way that would draw the attention of a distant telescope. The monster retires. After roughly 10,000 years, the magnetic field has decayed to a level that, while still enormous by terrestrial standards, perhaps a few trillion Gauss, still 1,000,000 times the strongest field ever produced in a laboratory, is no longer sufficient to drive the extreme phenomena that define the magnetar phase. The crust no longer fractures. The magnetosphere no longer reconnects catastrophically. The X-ray emission fades to the point of undetectability. What remains is an ordinary neutron star, perhaps observable as a faint radio pulsar if its geometry is favorable, perhaps entirely invisible if it is not. The vast majority of magnetars that have ever existed in the Milky Way, and the estimates suggest there may be more than 1,000,000 of them, accumulated over the galaxy's 13 billion-year history, have long since completed this transition. They are out there, scattered through the galactic disk, cold and dark and silent, monuments to a violence that burned out before the first humans walked the Earth. There is one caveat to this picture, and it is an unsettling one. In 2009, astronomers studying a magnetar called SGR 0418+5729, the object with the lowest apparent surface magnetic field of any known magnetar, about 100 times weaker than its typical counterparts, discovered that beneath that modest exterior, the star was hiding a far stronger field. XMM Newton observations revealed localized regions on the magnetar's surface, spanning only a few hundred meters across, where the magnetic field spiked to 10 to the 15 Gauss or beyond, rivaling the strongest fields ever measured. The dipole field, the large-scale, smoothly varying component that spin-down measurements detect, had decayed to an unremarkable level. But the internal field, twisted and concentrated into small-scale structures, was still immense. The implication was immediate and uncomfortable. If a magnetar can retain a powerful internal field long after its dipole field has faded below the detection threshold, then the assumption that faded magnetars are safe may be premature. Andrea Tiengo, the lead author of the study, noted that the finding confirmed a possibility that theorists had been considering. Any pulsar might conceal a magnetar-strength field in its interior without displaying it as a strong dipole field. As a result, all pulsars might switch on and become magnetars for a while. The boundary between a retired magnetar and an ordinary neutron star might not be a wall. It might be a door. And occasionally, under the right conditions, it might open again. Whether this actually happens, whether a seemingly quiet neutron star can reactivate its magnetar phase after years or centuries of dormancy, remains one of the open questions in the field. The theoretical machinery permits it. The observational evidence hints at it. But no confirmed case of a full reactivation has been documented, and the sample size of known magnetars is too small to draw firm conclusions. For now, the retired magnetars drift on in silence, their secrets carried in fields we cannot see, their potential locked behind a threshold we do not fully understand. What we do understand is the shape of their story, and it is a shape that rhymes with everything else the universe builds. Stars burn for billions of years and die. Galaxies form, evolve, and will eventually go dark. Even black holes, the most permanent-seeming objects in creation, will evaporate through Hawking radiation on timescales so long that writing the number would exhaust the available atoms in the universe. Nothing the cosmos builds is permanent, and the magnetar is simply the most dramatic example of that impermanence. The most powerful magnetic field in the universe, burning through its own energy in a span of time shorter than the history of human agriculture, leaving behind a darkness that will outlast the stars. We have traveled a long way together. We began with an explosion that crossed the galaxy and touched the Earth, a signal from an object so small that it could fit inside the boundaries of a single city, and so powerful that it blinded the instruments we had built specifically to observe the most violent events in the cosmos. We followed the story backward into the death of a massive star and the birth of something new from its collapse, a remnant so dense that a teaspoon of its matter outweighs every structure ever built by human hands. We traced the magnetic field from its origins in the dynamo of a newly born neutron star to its full, terrifying maturity at a quadrillion Gauss, a strength that deforms atoms, breaks the chemistry of life, and turns empty space into something that behaves like a crystal. We watched the crust fracture under stresses that no material in the universe can indefinitely contain, and we measured the consequences of that fracture from 50,000 light-years away. We learned that these objects can produce signals detectable from the other side of the observable universe, and that their influence on the vacuum itself has confirmed predictions that waited 80 years for evidence. And we learned that all of it, the fury, the reach, the strange quantum effects, the danger, lasts for roughly 10,000 years before the field decays and the magnetar goes silent. That is the portrait, the most dangerous object in the universe, rendered in full. But there is something that the portrait does not quite capture, and it is worth pausing here, near the end, to try. The study of magnetars is still young. The term itself is only 3 decades old, the observational confirmation barely more than 2, and the most significant discoveries, the FRB connection, the vacuum birefringence measurements, the youngest magnetar, have all come within the last few years. The field is moving quickly, driven by a new generation of instruments that did not exist a decade ago. IXPE is mapping the polarization of X-ray light from magnetar surfaces with a precision that would have seemed impossible in 2010. CHIME is detecting hundreds of fast radio bursts per year, building a statistical picture of FRB populations that will, in time, reveal how many of them trace back to magnetar sources. The European Extremely Large Telescope, currently under construction in Chile's Atacama Desert with a primary mirror nearly 40 meters across, will be capable of measuring the polarization of visible light from neutron stars far fainter than any observed to date, extending the test of vacuum birefringence to an entirely new sample of objects. Each of these instruments is, in its own way, a conversation with the magnetar, a question posed across thousands of light years, answered in photons that carry information about conditions that cannot be recreated in any laboratory on Earth. And that is the quality that elevates magnetars beyond their title as the most dangerous objects in the universe into something rarer and, in a certain light, more important. They are laboratories. Not laboratories we built, laboratories the universe built, operating under conditions so extreme that they test the foundations of physics in ways we cannot replicate by any other means. The behavior of matter at nuclear densities. The structure of the vacuum in magnetic fields 100 billion times beyond our technological reach. The mechanics of magnetic reconnection at energies that make solar physics look like a rounding error. The coherent emission mechanisms that produce fast radio bursts, mechanisms we do not yet fully understand, operating in environments we cannot directly observe, producing signals we can barely detect. Every magnetar observation is a data point from a regime of physics that is otherwise entirely theoretical, and the accumulation of those data points is, slowly and steadily, rewriting our understanding of how the universe behaves at its most extreme. The neutron star interior is a case in point. We do not know, with certainty, what happens at the center of a neutron star. The densities exceed those of an atomic nucleus, which means that the matter there exists in a phase that has no terrestrial equivalent and cannot be produced in particle accelerators. It may be a superfluid of neutrons. It may contain exotic particles, hyperons, kaon condensates, that alter the equation of state in ways that would change the relationship between a neutron star's mass and its radius. It may, at the highest densities, dissolve into a soup of free quarks, quark matter, a phase of existence that has been theorized but never confirmed. Magnetars, because their extreme fields drive observable phenomena that are sensitive to the internal structure of the star, the frequencies of seismic oscillations after a giant flare, the thermal evolution of the surface, the precise pattern of spin-down behavior, are among the most powerful probes of this hidden interior. The starquakes that make them dangerous are also the events that make them scientifically irreplaceable. There is a tension in that, and it is a tension that runs through the entire history of our relationship with the cosmos. The things that are most dangerous to us are often the things that teach us the most about reality. Supernovae can sterilize solar systems, but they also forge every element heavier than iron and distribute it across the galaxy for new stars and new planets to incorporate, including the planet you are lying on right now, which is made substantially of supernova debris. Black holes warp space-time to the point of breaking, but their event horizons are where the deepest questions about the nature of gravity and quantum mechanics collide. And magnetars, the objects that can crack their own surfaces and send killing radiation across interstellar distances, are the universe's only natural laboratory for testing quantum electrodynamics in the strong field limit, for probing the equation of state of matter at supranuclear density, and for studying the astrophysics of coherent radio emission under conditions that nothing else can produce. The danger and the knowledge are not separable. They come from the same source, the magnetic field, and they are expressions of the same physics. The field that cracks the crust is the same field that drives the seismic oscillations that reveal the star's interior. The field that polarizes the vacuum is the same field that lets us test QED in a regime Heisenberg could only calculate. The field that could strip the ozone from our atmosphere is the same field that produces the fast radio bursts that are, right now, teaching us something new about the universe with every detection. Perhaps that is the deepest thing a magnetar has to tell us. Not that the universe is dangerous, we have known that for as long as we have looked up, but that the universe does not distinguish between creation and destruction the way we do. The same processes that threaten life are the ones that make it possible. The same forces that could end a civilization are the ones that build the elements that civilization is made of. And the same magnetic field that makes a magnetar the most dangerous object in the known universe is the one that makes it, simultaneously, one of the most valuable. We are the only species on the only planet we know of that has ever detected a magnetar. We are the only arrangement of matter in this corner of the galaxy that has looked at a 20-kilometer sphere of neutrons on the far side of the Milky Way and understood what it was, how it worked, and why it mattered. That understanding did not protect us from the December 27th event. Nothing could have, and nothing needed to, because the distance was large enough to reduce the danger to a measurable but harmless perturbation of the ionosphere. But the understanding itself is not nothing. It is, in a way that is difficult to articulate without sounding sentimental, the entire point. The universe has been producing magnetars for 13 billion years, in galaxies scattered across the observable cosmos, and for all of that time, not one of them was understood. They flared and flared again in an emptiness that did not know they were there. And then, on a small rocky planet orbiting an ordinary yellow star in the quiet suburbs of an unremarkable spiral galaxy, something began to listen. That is where this story ends, not with the magnetar, but with the listening. Somewhere in the Milky Way tonight, a magnetar is rotating in the dark. Every few seconds it completes one full turn, sweeping its magnetic field lines through space, the way a lighthouse sweeps a beam across the water, though there is no beam here that any human eye could see. The field extends outward from the surface in a complex architecture of loops and twists, shaped by currents deep in the star's interior, evolving so slowly that a human lifetime would not be long enough to notice the change. The crust beneath it is under stress. It is always under stress. But for now, the crystalline lattice holds. For now, the balance persists, the field pulls, the crust resists, and the magnetar turns once more in the silence. It has been doing this for centuries, or for millennia, depending on when it was born and how far along the 10,000-year clock has run. It may have thousands of years of activity remaining, or it may be in its final decades, the field approaching the threshold below which the crust will never fracture again and the emissions will fade for the last time. There is no way to know from here. The magnetar does not advertise its schedule, and the next giant flare, if there is one, will arrive without warning, the way they always do, crossing the galaxy at the speed of light to arrive at whatever happens to be in its path. But tonight, it is quiet. The field hums through the vacuum around it, polarizing the emptiness, bending the light of distant stars as it passes through the magnetized space. The surface glows faintly in X-rays, too dim to be noticed by any instrument not specifically pointed in its direction. The rotation continues, once every few seconds, steady, unhurried. And the dark of interstellar space wraps around the star the way it wraps around everything, patient and vast and old. Somewhere, on the other side of those light years, you are listening to this. The same atoms that a magnetar would reshape into unrecognizable needles are, in you, folded into proteins and memories, and the quiet electrical hum of a brain making sense of the cosmos. The iron in your blood was forged in a star that died before the sun was born, scattered across space by an explosion not so different from the one that created the magnetar we have spent these hours with. You are made of the same material, shaped by the same forces, born from the same physics. The magnetar turns in the dark, and you are here, and both of those facts are part of the same story. Let the silence settle now. Let the distance do what distance does, and hold the danger at arm's length, where it becomes not threat, but wonder. The magnetar will still be there in the morning, turning, humming, waiting. It does not need you to watch it. It does not need you to understand it, but you did, and that matters, even if the cosmos does not keep score. Rest now. The universe is vast and old and mostly empty, and the things that burn brightest within it burn briefly, and the darkness that follows is not an ending, but a stillness. The same stillness that sits between the stars, between the atoms, between one breath and the one that follows. Close your eyes. The magnetar turns. The field hums. The light that left it thousands of years ago is still traveling, still carrying its message across the void, indifferent to whether anyone is awake to receive it.